Hi guys, myself Dr. Hemawati Patil, Assistant Professor of Mathematics, Government First Grade College, Manhalli. Welcome to session 4 on sequences. In this session, we are going to study some more theorems on the sequence. Take one theorem. If limit as n tends to infinity xn is equals to L1 and limit as n tends to infinity yn is equals to L2, then prove that first one, limit as n tends to infinity kxn is equals to k into L1, where k being constant. And second one, limit as n tends to infinity xn plus yn is equals to L1 plus L2. And third one, limit as n tends to infinity xn minus yn is equals to L1 minus L2. Fourth one, limit as n tends to infinity xn yn is equals to L1 L2. And last one, limit as n tends to infinity xn divided by yn is equals to L1 divided by L2. So here the two limits are given. If limit as n tends to infinity xn is equals to L1 and limit as n tends to infinity yn is equals to L2, then in these cases you have to prove these 5 results. Let us take proof. First one, so we have to prove here k into xn is equals to k, limit as n tends to infinity kxn is equals to k L1. Let us take proof. Let epsilon greater than 0 be given. Then see here what we want to prove. We want to prove limit as n tends to infinity kxn is equals to k L1. You know the definition of this limit. So it means here you have to prove mod of kxn minus kl1 is less than epsilon, then we can say that this limit exists. This limit is equals to kl1. So let us take here, let epsilon greater than 0 be given. Then this implies mod of, let us consider here mod of kxn minus kl1 is equals to, take k common. When it is xn minus L1 is equals to, we can take a k common here, that is mod k into mod xn minus L1. Take this one as equation number 1. And since limit as n tends to infinity xn is equals to L1, this is given, and this implies epsilon greater than 0, there exists m belongs to n such that mod of xn minus L1 is less than epsilon divided by mod of k plus 1. See here, so it is here it is given, no, this is mod of, which is less than epsilon divided by mod of k plus 1. So equation 1 implies here, equation 1 is our equation 1 is this one. So mod of kx1 minus kl1, if you open this bracket you will get like this, which is less than mod k as it is, and in place of mod xn minus l1 we can take this one as here epsilon divided by mod k plus 1. So this implies what? This implies mod k xn minus kl1 is less than epsilon. Why it is less than epsilon means here, if it is less than mod k divided by mod k plus 1, we know mod k divided by mod k plus 1 is always, which is always what? Which is always less than 1. So if it is, if you multiply any number epsilon with less than 1, then this definitely this is again less than epsilon, which is less than epsilon only. So we can take this one as here less than epsilon, because here mod k divided by mod k plus 1 is always less than 1. So less than, so this becomes what here? Less than 1 into epsilon, which is less than 1 into epsilon. So we can take this one as here 1 into epsilon as epsilon we can take. This is less than epsilon for all n belongs to, for all n greater than equals to m. So what this implies, let us apply the definition. This implies limit as n tends to infinity kxn is equals to kl1. This is the first proof. We know this. How we got this one means here we know by the definition. We know by the definition, if mod xn minus l is less than epsilon for all n greater than or equals to m, then we know here, then what we have? We have limit as n tends to infinity xn is equals to l. This we know. So for that we apply this definition. So this is about the first proof. Let us take one more second proof. Let epsilon greater than 0 be given. Then since it is given. It is given limit as n tends to infinity xn is equals to L1 and limit as n tends to infinity yn is equals to L2. These two are given. So for this, let us consider there exist m1 and m2 belongs to n such that in second result what we want to prove? We want to prove limit as n tends to infinity xn plus yn is equals to L1 plus L2. So let us take here mod xn minus L1, because from this we can take mod xn minus L1 is less than epsilon by 2 we can take, because here epsilon is very small number which is greater than 0, so we can take this one as here which is less than epsilon by 2 by the definition. And similarly limit as n tends to infinity yn is equals to L2, this implies here mod of yn minus L2 is less than epsilon by 2 for all n greater than or equals to m. Now let us combine these two, that is therefore consider here, you see, always I told you, you have to see the result, what we want to prove. We want to prove mod xn plus yn is equals to L1 plus L2, no? So you consider that only. Mod of xn plus yn minus L1 plus L2 is equals to, you take these two. Why you have taken this one means because we want to prove this one. So whatever you want to prove, you have to take that one only. This is equals to we want to prove, no? Take this one xn minus L1 plus yn minus L2. Now if you open this mod, if you open this mod, what happens here? It is, this one I told many times here, it is if mod z is less than, if mod z is less than a, if mod z is less than a, then what this implies here? If you sorry, it is not this one. If mod of a plus b is less than or equals to, we know, mod a plus mod b. So for that, if you remove this mod, it becomes here less than or equals to mod xn minus L1 plus mod yn minus L2. So from this we have here, this is less than epsilon by 2 and this is also less than epsilon by 2. So epsilon by 2 plus epsilon by 2 is equals to epsilon. Mod of xn plus yn minus L1 plus L2 is less than epsilon. So this means for all n greater than or equals to m. So this means what? This means limit as n tends to infinity xn plus yn is equals to L1 plus L2. This is again from the definition of a limit. Let us prove third result. In third result, we want to prove mod limit as n tends to infinity xn is equals to L1 and limit as n tends to infinity yn is equals to L2. Then you have to prove limit as n tends to infinity xn minus yn is equals to L1 minus L2. So for that, let us take here, let epsilon greater than 0 be given. Since it is given, limit as n tends to infinity xn is equals to L1 and limit as n tends to infinity yn is equals to L2. This is given. Then this implies there exists m1 and m2 which belongs to n such that mod xn minus L1 is less than epsilon by 2 for all n greater than or equals to m1 and mod yn minus L2 is less than or equals to epsilon by 2 for all n greater than or equals to m2. Let us take m as maximum of m1 and m2. Then we can take these two as here. Mod xn minus L1 is less than epsilon by 2 and mod yn minus L2 is less than epsilon by 2 for all n greater than or equals to m. So this implies here, let us combine these two. That is, let us consider mod xn minus yn minus L1 minus L2. You just consider this one because you want to prove this one, no? So this is equals to, you arrange the terms, mod xn minus L1 minus, you take common, yn minus L2. Then if you, again I told you, if mod x minus y is always less than or equals to mod x plus mod y. So this can be taken as here, which is less than mod xn minus L1 plus mod yn minus L2. And from these two we can say that here it is, this is less than epsilon by 2 and it is also less than epsilon by 2. So sum of these two is again epsilon. Therefore mod xn minus yn minus L1 minus L2 is less than epsilon for all n greater than or equals to m. So this implies what? This implies the definition limit as n tends to infinity xn minus yn is equals to L1 minus L2. This is the proof of third theorem or third result. Let us prove fourth one. In fourth one, what we want to prove? We want to prove here limit as n tends to infinity xn into yn is equals to L1 into L2. Let us consider here, let epsilon greater than 0 be given. Then let us consider mod xn into yn minus L1 into L2 is equals to mod xn yn. What you have to do is here, you just add and subtract L1 y1. Subtracted L1 y1 and added L1 y1 and this minus L1 L2 as it is. Now again you know this mod a plus b is always less than or equals to mod a plus mod b. So this can be taken as here, first you take yn common, then it is xn minus L1 plus in these two L1 common, it is yn minus L2. And if you apply here, mod a plus b is always less than or equals to mod a plus mod b. So it is less than or equals to mod yn into xn minus L1 plus mod L1 yn minus L2. Take this one as equation number 1. And it is less than, you take mod yn outside and this mod L1 is also outside and write the remaining terms. Since the sequence yn is convergent and it is bounded, we know here it is given, since this yn is convergent, it is bounded, therefore there exists a positive real number k such that mod of yn is less than k for all n. So since here limit as n tends to infinity xn is equals to L1 and limit as n tends to infinity yn is equals to L2. Here let us take this one as equation number 2. So then there exists m1 and m2 belongs to n such that mod xn minus L1 is less than epsilon by 2k for all n greater than or equals to m, and mod yn minus L2 is less than epsilon by 2 into mod of L1 plus 1 for all n greater than or equals to m. I'll tell you why we have taken this one as here 2k and here it is 2 into mod of L1 plus 1. So because here you want to get the result, you have to take like this, because here in this one in equation, this one in previous equation we have seen here, this one is here we have in second term we have mod L1 is outside, isn't it? So in first term what we have here, we have 2 here, it is k is outside, mod k is we have outside. So here we have mod L1 is outside. To remove that mod L1 you have to divide here it by mod L1 plus 1, because here mod L1, just now I told you mod L1 divided by mod L1 plus 1 or anything, it is a divided by mod a plus 1. A divided by a plus 1 is always less than 1, we can take, no? So for that we can neglect this term, we can take only epsilon by 2. Here also it is mod k is there, mod xn minus L1. In previous case we have seen here it is mod k. So to remove mod k we have taken here divided by k. So let us take m is maximum of m1 and m2, and this implies mod xn minus L1 is less than epsilon by 2k and mod yn minus L2 is less than epsilon divided by 2 into mod L1 plus 1 for all n greater than equals to m. So equation 1 implies mod xn yn minus L1 L2 is less than epsilon by 2k into k, it is, we know k we have taken outside here, then plus this one is mod L1 as it is, and what we have here, mod yn minus L2. In place of mod yn minus L2 we have to take epsilon divided by 2 into mod L1 plus 1, because here we have taken this one, and this is for all n greater than equals to m. So now which is less than here, k get cancel, epsilon by 2 plus mod L1 divided by mod L1 plus 1 into epsilon by 2 for all n greater than equals to m. So just now I told you a divided by a plus 1 is always less than 1. So we can take this is less than 1 means which is less than epsilon by 2 also. So it is we can take this one as here which is less than epsilon divided by 2 plus epsilon divided by 2 for all n greater than equals to m. So this is what? This is sum of these two is again equals to what? This is equals to, if you take this one as is equals to, this is equals to here epsilon we can take, this one is equals to epsilon. So what this implies? This implies limit as n tends to infinity xn yn is equals to this one. If it is less than epsilon, then we can take this is equals to L1 into L2. This is the result of fourth condition or fourth theorem. Take last one. Here let epsilon greater than, what you want to prove here? We want to prove limit as n tends to infinity xn by yn is equals to L1 into L2. We want to prove this one. For that, let us consider 1 by yn. See here what we have done. We have splitted that one. What we want to prove here? What we want to prove? Here we want to prove limit as n tends to infinity xn divided by yn is equals to L1 by L2 we want to prove. So to prove this, we have splitted this one as here limit as n tends to infinity xn as it is. Only 1 by yn we want to prove. 1 by yn is equals to 1 by L2, and after that we can take xn equals to L1. We will take this one directly. So for that you just consider 1 by yn minus 1 by L2, which is equals to, take LCM, xn, yn into L2 is LCM, and write the remaining term L2 minus yn. It is equals to, here it is, we can take minus sign common. It is mod of L2 minus yn divided by, this is mod yn into mod L2, and we can take minus sign common here. If you take, again I told this one many times here, if mod minus a can also be written as mod a, that is if you take L2 minus y1 is same as y1 minus L2, it is, there is no any difference here. We can take this one as mod yn minus L2 divided by mod yn into L2. So since here limit as n tends to infinity, yn is equals to L2, therefore limit as n tends to infinity, mod yn is equals to mod L2. This we studied in second theorem. If limit as n tends to infinity xn is equals to L1, then limit as n tends to infinity mod xn is mod L1. This we studied. So we can take this one by second theorem. Now choose here epsilon is equals to mod L2 divided by 2, which is greater than 0. For all there exists m1 belongs to n such that mod of mod yn minus mod L2 is less than mod L2 divided by 2, because here which is less than, which is by the definition which is less than epsilon we know here, and that is epsilon is nothing but mod L2 divided by 2 for all n greater than or equals to m. So now this implies here, if you open this mod, we know this again. We know if mod z is less than, we know this. If you remove mod, what happens? If you remove mod, that is, we know this. If mod z is less than a, then z is greater than minus a, less than plus a. So like that only. We have here, we remove this mod. So we remove this mod. What happens here? It is mod of yn minus mod L2 is greater than minus mod L2 by 2 and less than plus mod L2 by 2 for all n greater than or equals to m. I now take this minus mod L2 in this side, it becomes here, this is minus, this is become plus mod L2 minus this one mod L2 divided by 2 as it is, and mod yn as it is, which is less than mod L2 divided by 2, and this one is plus mod L2. This is for all n greater than or equals to m. So now this implies here, difference of these two is 1 minus 1 by 2 is 1 by 2. It is mod L2 divided by 2, which is less than mod yn, which is less than sum of this 1 plus 1 by 2 is 3 by 2. It is 3 by 2 into mod L2 for all n greater than or equals to m1. So that is what we have here. Here we have mod yn is definitely greater than mod L2 divided by 2. If you take reciprocal, it becomes 1 by mod yn is less than 2 divided by mod L2. We know here if a is greater than b, then this implies 1 by a is less than 1 by b. So since limit as n tends to infinity yn is equals to L2, this implies there exists m2 belongs to n such that mod yn minus L2 is less than mod L2 square into epsilon, but this is all we have to choose ourselves, because here according to our result you have to choose this one here. That is, if you take this one divided by, in the equation 1 we need all these values. So for that you have to choose like this, mod L2 was square into epsilon by 2. So let us take m is maximum of m1 and m2. Then equation, this is equation 3. Equation 2 and 3 becomes here. Equation 2 and 3 becomes, which is 1 by mod yn is less than 2 by mod L2, and mod yn minus L2 is less than mod L2 whole square divided by 2 into epsilon for all n greater than or equals to m. So now equation 1 implies, equation 1 is what? 1 divided by mod 1 by yn minus 1 by L2 is less than, what we have equation 1? Equation 1 is, this is mod yn minus L2 divided by mod yn minus L2 divided by mod yn into mod L2. I'll write equation 1 here. So equation 1 is, equation 1 I'll write here. Equation 1 is 1 divided by this is mod 1 by yn minus 1 by L2 is equals to mod yn minus L2 divided by mod yn into mod L2. So this value how to substitute. Here it is, here we have, which is equals to mod yn minus L2. Mod yn minus L2 is less than mod L2 square divided by 2 into epsilon by 2 here. And this one, 1 by mod yn. Here we have 1 by mod yn is less than 2 by mod L2. That you have to write 2 by mod L2, and this 1 by mod L2 as it is. I hope all of you understood why we have chosen this one as 2 by mod L2 and this one as 2 by this one mod L2 whole square into epsilon by 2. To get the result you have to choose like this. So now what happens here, 2 to get cancelled and mod L square get cancelled. So only epsilon remains. So mod of 1 by yn minus 1 by L2 is less than epsilon. So it means limit as n tends to infinity, 1 by yn is equals to 1 by L2. This is equation number 5. We want limit as n tends to infinity, xn by yn is equals to limit as n tends to infinity, this xn you keep as it is into 1 by yn. We can apply limit to both the terms separately. So limit as n tends to infinity xn into limit as n tends to infinity 1 by yn. So this implies this limit is L1 it is given, and this limit we proved here as 1 by L2. So if you combine these two, you will get what? You will get 1 by L1, that is L1 divided by L2 we got. So thus what we have? We have limit as n tends to infinity. What we proved? We proved here limit as n tends to infinity xn divided by yn is equals to L1 divided by L2. This is about the fifth theorem. So in this theorem we studied 5 points. So this is the last one. I hope all of you understood this one. If you not understood, then you can, if you have any doubt, then you can put comment in a comment box. Thank you very much for being with me in this session. Thank you.